It's now time for the problem session for Michael Gekhtman's course. So you'll probably solve a few questions, and also if you thought of additional questions for Michael over lunch, it's also a good time to ask them.
Okay, so it's an unstructured part of the mini course. So the easiest way would be if someone wants to solve a problem or give an idea and we can do it together, or just ask any questions preferably related to the lecture, but not necessarily. Huh? Yeah. Well, so there were a couple of elementary ones. I think the first one was if A is invertible, totally positive, then let me put it this way: 1 minus 1, 1 minus 1, and so on. The inverse 1 minus 1, 1 minus 1, and so on is also TP. Huh? Sure. Sorry, thank you. Yeah. So that was one. There was one about 3 by 3 positive entry-wise A with all 2 by 2 minors positive but negative determinant. Was there something else? Oh, yes. So give an example.
Before this, I have a question.
Yeah, sure. Yeah.
So we were looking at Jacobi matrices.
Right.
And you said that the Jacobi matrix is totally.
You said that a Jacobi matrix is totally non-negative if and only if all the AI, BI, CI are positive, and determinant of the principal minor, all principal minors are positive.
Yeah.
So I got a bit lost there. So what you showed was that, so you basically took a diagonal, you conjugated by a diagonal matrix.
Right.
Such that it becomes symmetric.
Right.
And then you said it's still positive so I think you were proving the implication this way?
So I did that to show spectral properties of this of this matrix.
So you did not.
Yeah, for total positivity, you don't really need. You need to conjugate. It doesn't have to be symmetric.
Okay.
Yeah, for total non-negativity.
So what is? So could you give us the idea of the proof there?
Yes. So I guess so. We're talking about Jacobi matrix. So let me remind you what it is. So I think I put them like this: B1, Bn, B1. n minus 1, C1, Cn minus 1, and well, we immediately assume that all the entries are positive, and this is a just slight generalization of what Professor Tsujimoto had in his talk, and actually it can be conjugated to that form as well, with all ones in the diagonal. And so here, we just need to look at all minors, again, that are not combinatorially zero or trivially zero, as we said. Maybe it's a good idea just to look at an example. So let's do an example, and I don't even need, because I'm talking about combinatorial non-zero properties. So I'll just put dots and zeros. Let's say it's 5 by 5. 1, 2, 3, 0, 0, 1, 2. Right, so it's a tridiagonal matrix. And so what you can see is the following. So first of all, you can try to explore what minors can be non-negative, right? So for example, or can be non-zero. So this one is obviously 0 because it has a row of zeros, and so this is pretty much the extent of it. So if you find any minor with a row of zeros, then a column of 0, it will be 0. So the rest of them one can find out. So let me try to indicate a minor which is not like that, but then let's see what's going to happen with it. So I'm going to take 1, 2, 4, right, and let's say again 1, 2, 5 maybe. Okay, so let me just mark things in blue. So it's not a principal minor, but what you will see that it will break 1, 2, 4, 1, 2, 5, right? What you can see is that it will break into the product of a principal minor and some of diagonal elements. So as a hint, so if you look at minors which are almost principals that do not stray from being principal too much, meaning that the distance between corresponding indices is for row and column is either 0 or 1 or -1. Those minors will be product of principal minor and sub or super diagonal entries, and the rest of them will be 0. Another way to do it, again, because I'm going to exploit Professor Tsujimada's talk, is the following. So suppose I have all principal minors positive. So in fact, it's enough to have all leading principal minors positive. What does it mean? It means that I can factor this matrix into the product, let's call it G minus G plus, where, well, I can decide how to do it. So I can say that this G minus, again, I'm going just to use dots because it's what important. G minus is lower diagonal and lower bidiagonal, and G plus is upper bidiagonals, but it's my choice where to put all the diagonal elements, so I will put them over here, right? Because this matrix has all principal minors positive, as we discussed, it has, well, that's enough for factorization. All of these entries are going to be pluses because principal minor is just the product of the consecutive entries here, right? And then the rest is kind of clear because, yes, you will have this guy's positive necessarily because of factorization, this guy's positive necessarily, and because of Binet-Cauchy property, everything that is not 0 is going to be positive. So this is actually an important part, that any totally non-negative invertible matrix has Gauss factorization in any order that you would like. Well, I mean, there are just 2 orders. But,
so here you're using something weaker. You're just using leading.
Well, so this is another property which is true both for totally positive and positive definite matrices. If leading principal minors, in fact, if any nested family of principal minors is positive, then all of them are positive. Nested family meaning I can I can say, well, start here and then here and then here. And so that's enough. And this has something to do with cluster algebra. So there is a finite type cluster algebra related to this, and this just saying that a nested family of principal minors form a cluster in the corresponding cluster algebra, which we can actually talk about. Oh, I was planning to talk about this a little bit later. Right. Yeah. Was there something else? Oh yeah, there was about Pascal triangle, or that if we know that this matrix, so on, is totally non-negative, how to derive from it that this matrix so on, yeah. Is it 4, 6, 4, 10, 20, and so on, is totally positive. And yeah, there is a purely combinatorial way to do that. Relies on some identities. So all of this are pretty elementary. And actually, this could be a hint to this problem. So again, I don't know how exactly to do this, but you can think about these hints. You can ask me more questions, or a graduate student, former graduate student, long before graduate student. Yeah, no, it's fine. If there are volunteers, I'll welcome.
I was thinking of using Mathematica to just generate such a matrix.
Right.
So, but it seems overdetermined, right? Because I have 9 entries, so I have 9 things I want positive.
Right.
And I have 9 2x2 principal minors, 3 times 3. So I have 9 more inequalities.
Right.
So I have the negative determinant, so I have like 19, twice 9.
Yeah.
So 19 inequalities for 9 variables.
Yeah. So this is a very good point, because it will bring us to what I was going to start the next lecture with. So how do you test total positivity? So you have how many minors you have for a matrix. So you can choose.
Choose k squared. For each k, you have to choose.
Right. Yeah. Yes. Exactly. Yeah, and choose k squared, right? And then so that will give you, well, because of, again, one of these nice identities, you have well, but you have to do it for all sizes, right?
Yeah, so when you solve and choose k squared, you get 2 and choose it.
Yeah. You'll have, yeah, so it's an exponentially growing number of minors, and it's very impractical to check them all. And in fact, one of the results we're going to talk about tomorrow is that in fact you don't need to check more than n squared, which is a dimension of the space of matrices. So the same story goes for this example. Maybe you don't need to start with inequalities. Maybe you have to start with something which is already totally positive, and maybe factor it in a smart way, and then deform it a little bit. So so one idea, and again we can explore it. So if I have a matrix, since I want all 2x2 to be positive and it's invertible, it again has Gauss factorization. So maybe let's try the following. So I'll do Yeah, I'm doing an example. So first I want to start with something positive. Well, here we don't need to check much. So this will be, I mean, something totally non-negative, right? This is totally non-negative. I am going to do, huh?
The 2 by 2 is negative. 1 minus 2.
Sorry, 1 minus 2. So I'm doing it the opposite. Yeah, this is what I meant. Sorry. Yeah. Well, but in fact, I can put anything here, which is totally. And then let's do 1, 2, 3, 1, 2, 1 here. All right. So that's no good because if I multiply them, no good for our example. If I multiply them together, then I'll get something which is totally positive, right? So
this is not close, I mean, this is not bidiagonal, right?
no. It's because I want it to be, I want the result to be term positive, and then also all 2 by 2 minors I want to be positive, no zeros. Okay, so. Well, how can I destroy this nice property, but not completely? What can I do? Let's plug something in the middle. Well, something simple. So again, if I put something positive here, this is going to hurt me. Well, so let's put here minus epsilon and see what happens. And what happens is the following. So. This epsilon will be involved in computing some matrix entries, but it will not ever come as a single term. So we'll have, if you compute any matrix entry in this product, you'll get something positive minus epsilon times something. And the same story for 2 by 2 minors. You'll get, well, in any, using Binet-Cauchy, if you consider any 2 by 2 minors, either epsilon will not be involved at all, or it will be involved in only one of the terms. Okay? So if it's involved in more than in an expression with more than one term, I can make epsilon small enough so that the result is still positive. However, the determinant of A, as we all know, is simply minus epsilon, so we're done. So you can actually generate a lot of them. Again, I don't want to give it away today, but tomorrow we'll do it with pictures. It also maybe illustrates one important difference between totally positive, totally non-negative matrices, so which are minors can be positive, which can be zero. And if you ask a seemingly similar question, suppose you have a matrix and you want to know that all minors are non-zero, right? So determining distinguishing such matrices is an NP-hard problem. Here, it's everything can be computed pretty quickly, but if you just worry about zero non-zero pattern of determinants, then it's completely wild. Yes?
Suppose we're given that a matrix is totally positive and we're interested in the smallest, and we're interested in the value of the smallest minor. Is that also computationally hard?
Smallest minor. So good. That's a good question. Yeah. So I think so. And I will answer. So I'll give an answer and try to justify it. So, but I'm trying to give it on the spot. So I think any minor. So you give an minor, because one thing is that any minor can be the smallest minor, and the reason for that is the following. So you can find coordinates on the set of totally positive matrices, coordinates, which consists just of certain minor, collection of minors. So n square minors, but they cannot be just arbitrary. They can be selected in a very particular way. But for any given minor, you can find such a coordinate chart to which this minor belongs. And since they're coordinates, they can take arbitrarily positive values. So any one of them will be the smallest, could be the smallest. So how to, but it still doesn't answer your question, because your question is the matrix is already given. So, yeah, so sorry, I'm not sure, but yeah, again, one thing is for sure that any one of them could be the smallest. But yeah, I'll have to think.
It's not a very well-motivated question or anything. It's just something that came to mind.
Yeah, no, it's okay.
So there's no obvious bounds that you can give, say, minor of, I mean, one minor is nested inside another. Can you say?
Oh, yeah, that we can say about, so we have an expert here. Yeah, right. So this is more about maybe determinantal inequalities. And you can say a few things. So maybe I can, I don't know. Yeah, yes, there is that too. So maybe I'll comment on that and also on this nested minors. So about Brad decomposition. Okay, so let's yeah, and this will be useful tomorrow. So I'll start with Brad decomposition. Right? So we're just talking about matrices, but this can be done for any reductive group. So we know that there is this decomposition into disjoint union of GLN into so-called Brouwer cells. So I'll explain everything here. So B plus is just invertible upper triangular matrices. W is a permutation matrix. Okay, so there are various versions. For example, the two that one can use, so similar. So B minus is invertible low triangular matrix. So this is union over W. This is union over V. Okay. So two decompositions into disjoint unions of Brouwer cells. So what you can do, and this was one of the motivations for both finding criteria for total positivity and also for the discovery of cluster algebras. So what you can do, you can consider intersection of two such things. Right, so you consider intersection of two such things. It's no longer a cell. So we're working over reals, right? It's no longer a cell. Cell topologically, yeah. So, so in fact, one of this motivational question was asked by Arnold, and that's the number of connected components. Yeah, find the number of connected components in this. However, if we assume that we want an intersection of this set with a set of totally non-negative matrices, okay, then it is, in fact, diffeomorphic to the positive real line times the length of the first permutation, so the minimal number of transpositions, plus the length of the second permutation, plus, well, the rank of the correspondingly algebra. So, So let's just do an example, right? So just let's check that the counts are correct. Yeah, everything is over R because we're talking about positive things. So let's check that the count is correct. So let's do, so this is the longest permutation. So longest permutation is the one that is represented by this matrix. And the way it can be written, one of the ways, but the length doesn't depend on that. So if we consider elementary transposition, so 1 and 2, and then you do S2, S1, and then S3, S2, S1, and so on, Sn minus 1, and so on, S1. So the length is equal n choose 2, or n minus, right, over 2. So what is the dimension then of G W0 W0? It's twice n times n minus 1 over 2 plus n, which is n squared. So totally positive matrices are just diffeomorphic to R plus to the power of n squared. And again, one of the ways to coordinatize that is by choosing appropriate family of minors, and this is a subject of tomorrow. But maybe I should mention much harder questions. This was called Fomin-Shapiro conjecture that was proved by Patricia Hirsch and then generalized by Lam, Galashin, Karp, and Lam for positive Grassmannian. So you can then ask a question: what is topologically the closure of this set? Okay, so and you want to say this is an open, was this diffeomorphic to an open ball in natural conjectures, and the closure is diffeomorphic to a closed ball. Of course, there is no guarantee, because if you consider circle without a point, closure will be no longer a closed ball. But in fact, it is true, the closure of this set is a closed ball, and in fact, all these things together, they form CW complex. This was the extent of Fomin-Shapiro conjecture that was proven. Yeah, so yeah, you quickly get from these questions to quite complicated ones. Another thing that I may mention is that, so what is the answer to Arnold's question? I don't remember offhand the full answer, but and this is Shapiro, Weinstein, and Zelevinsky. In a series of papers, they showed that generically, in GLN, the number of connected components is equal 3 times 2 to the n minus 1. And this 3 here shows that this is not a trivial question, because if the number of connected components is not a power of 2, then something more complicated is going on there. Generically means that if n is large enough, if this W and V are, just sufficiently complicated. There is an explicit way to describe it, but it will lead us astray. And then similar questions can be asked for all reductive groups, and in a simply laced case, it was done by this group of people, and then in non-simply laced case, so yeah, it's very personal to me, because this was our first 3 people collaboration with Alex Shapiro and with Alex Weinstein and Misha Shapiro, and we did it for non-simply laced case. For example, for F4, the answer generically is 80 connected components. So you reduce this question to counting to counting some orbits of some finite group acting on Dynkin diagrams, but it all has counterparts in the cluster algebras. Yeah, sir, but that was your question. But now back to this arrangement of minors and what can and cannot happen to them. Let me erase something. So there are this classical determinantal inequalities. Okay, so I may confuse the names of them, but there are people here to correct me. So I think one is due to Adam R, saying that determinant of A is less or equal than product of diagonal elements. So, okay, so it's valid for positive definite matrices, totally non-negative matrices, then some other matrices like M matrices, and so on. Okay, so then there is feature inequality, right? Am I correct? This is Adamar. Thank you. Which says the following. So suppose I have a subset of indices in indices from from 1 to n, and then I have another inequality from which this one will follow. Determinant of A is less or equal than determinant of A, so principal minus I and I, and A, the complement of I. So again, so this one then will follow from this one by induction eventually, right? Again, valid for all these cases. And then there is another one called Kotylansky, from which the further two will follow. This is this was published in Ukrainian Mathematical Journal, so it's a long time ago. But I think after I was born, but barely. Yeah, so, and this is a similar story, but now you have two index subsets, I, J, in 1, n, and then determinant of A is less or equal than the product of determinant of A with index set I intersect J, I intersect J, times determinant of, what is it? Is it a union? Or, well, union, yeah. Yeah. Well, no, not the union, but union minus intersections. Yeah, no, sorry. How does it work? Yeah, union is on this side. Yeah, see? A little bit. So there is an overlap in them. There could be an overlap in them. I think it's I think it's easier to do it this way. So if there is an overlap, then okay. Determinant of I union J, right? And determinant of A I intersect J. Union means that I'm not repeating indices. Yeah, and then here it should be so that something like I minus J and J minus I, the complement. Okay. I minus J or I minus intersection, something like that. Sorry. Yeah, my excuse is that I haven't been, I haven't prepared it. But so something of this sort that you can easily fix and from which this other two follows. So there are these inequalities for and again, it's valid for positive definite and totally non-negative. But for totally non-negative, you can do this for non-principal minors as well. And so there are inequalities connecting non-principal minors necessarily of totally non-negative matrices, this multiplicative inequalities. So they're completely described in the case where you have product of two and product of two. This was started by Sean Follett and Charlie Johnson, and then we did it for principal minors, and then Mark Sandero generalized it for non-principal minors. But in general, if you consider just monomial in minors, and one is one monomial less than another monomial, this is still an open question. So all that we know that, and this we proved it with my graduate student Soskin recently, that this is a polyhedral. This inequalities form a polyhedral cone. How to describe it? It's not clear. There are recent indications that it's somehow related to tropical totally non-negative Grassmannian, but this is speculation at the moment.
But there's also interlacing theorems, right? So the
yes.
eigenvalues of a matrix and its
yes.
principal minor, largest principal minor.
Right. They are
eigenvalues
interlace, yeah.
So in particular, if a matrix is totally positive,
yeah.
then its smallest eigenvalue will be smaller than the eigenvalue of.
right. Yeah. Yeah. So again, this is a property they share with tridiagonal matrices.
So then that.
Yeah. It's true in general.
Yes. So therefore this now for I look at a minor and sub-minor.
Yeah.
Then the smallest eigenvalue of the minor.
Yeah, there are. There are properties like that. But I think the initial question was about any minor located anywhere. So that's yeah. About minors and about not necessarily principal minors. And it's clear that I can, for example, take, I can conjugate a totally positive matrices in such a way that some corner entry is, becoming as large as I want. So that's,
Yeah, no, I don't think this relies on this.
Yeah. To try to find the smallest value of a Plucker coordinate in a positive, totally positive Grassmannian. But it's, there are conjectures there. It's not, it's not resolved how to do it. Okay. That makes sense. So here is the same. No, I'm just saying that this is the same. I and J, because I, J, because you have to have a balanced set of indices. So each index has to appear here as many times as here. That's a necessary condition, but not sufficient. Right. So we need. Yeah, determinant is the smallest. And again, this particular inequalities we will see tomorrow how they easily follow from pictures. You don't need any analysis. So it's there are stronger positivity properties at place here. So in terms of this, in terms of coordinates of this sort, it turns out that if you express right-hand side and left-hand side in this way, and then consider the difference, then you'll just get a subtraction-free expression in terms of positive coordinates, and that's how it's evidently positive. But you have to choose this correct coordinates. And again, this is a precursor of cluster of Laurent phenomena in cluster algebras.
So I have a question.
Yeah.
All that you said was for totally positive square matrices,
Right.
But one can, of course, define totally positive
Yes.
rectangular
Yeah.
matrices. So is there a theory of that? Is
Yeah. Yeah. So I think the best way to do that is actually go through a notion of a totally positive Grassmannian. Okay. So which is yeah. So of course you can define everything like you said. You have a square, a rectangular matrix. All minors are positive. But the convenient way to do this is the following. So let's consider Grassmannian of k-dimensional subspaces. So k-dimensional subspaces in Rn. And so you can consider a representative here to be A, which is k by n full rank matrix. Right, so we draw it like this. And you can coordinatize it using Fluker coordinates. So pi I, where this is just determinant of A with all the rows and columns I1, IK. Right, so of course we have too many coordinates here, so subject to Fluker relations. And then inside this Grassmannian, you can consider the positive part. And this is the set of all elements in the Grassmannian such that A, so this is a representative. So A has all Flukers of the same sign. So if they're of the same signs, they can all be made positive. So so that's the set. So first of all, if it's a full rank, then you can find a representative here that has a form. So he'll have this permutation matrix 1 minus 1 and so on. And here I'll have some other matrix, let's call it B. So A is element of a totally, represents an element of a totally positive Grassmannian if B is just simply totally positive because there is a one-to-one correspondence between Fluker coordinates here and minors here. So square, non-squares, they all sit here. And then there is this rich theory which is developed by Postnikov that describes parameterization, coordinatization of these elements using planar networks in the disk, of which parameterization of totally positive matrices that I'm going to talk tomorrow about is a particular case. So, and again, there are coordinates here, not all of them, but there are coordinate systems here which are made purely of Plücker, just of Plücker coordinates, but you have to select them appropriately. Yeah, so this all exists. So spectral part is not relevant here because there are no eigenvalues, but to talk about, but yeah. All right, so we can solve this problem, but this will be just this will be just one line, just one identity. So very good. Yeah. Exactly, yeah. So, yeah, all you have to do is that A minus Ij is equal to 1 over determinant. Yeah, determinant of A, determinant of A, I complement J complementized minus 1 raised into power I plus J was also just sums of indices of I and J, and so multiplying by this matrix will just completely destroy this part, and that's it. Yeah. So that part is easy, and because of that, sometimes people talk about positive inverses of totally positive matrices, again, which can be represented diagrammatically, just yeah, with pictures. Of A. Yeah, of A itself. It's essentially you take a formula for the inverse and just replace it, replace small indices with capital for index sets, and that's it. Oh, so I is a collection of indices and J is a collection of indices, so you just add them all up. I want, yeah, well, yeah, I can, yeah, it's the same. Yeah, thank you. You can do this. Yeah. Yeah.
One thing that is not clear, suppose you have a matrix that is totally non-negative.
Right.
Is there a tiny perturbation that makes it totally positive?
Yeah, that's a good question. Yes. It's not trivial, but so no, not by single, because you may have a lot of zero. But actually, let's tiny in terms of the difference. Yeah, if you subtract, it will be small. So let's make such a matrix totally positive, right? So what you can do, you take J, and then we can make our tiny perturbation, but just multiplying it on one side by 1, 1, and so on, 1. And again, I'll take epsilon, but now epsilon is positive, and raise it into power n minus 2. And then on the other side, you do the same. And because of, again, Binet-Cauchy, this will fill up our matrix completely. and this is totally non-negative, this is totally non-negative, this is totally non-negative, you'll see that everything will be positive. But perturbation is small because epsilon is small.
I was thinking more in terms of when I heard his question.
Or additive is, so there are some theorems about so-called intervals of total positivity when you add something, but this is a little tricky because this property plays well with it's in spirit multiplicative, but there are these theorems about intervals of total positivity, and I can look them up and quote them more carefully, but so I think I'm almost sure that the statement is like this. So if you have two totally positive matrices, and one is entry-wise, so there is a relation between them. If there is a relation between them, which is again checkerboard relation. So A11 is less than B11, A12 is greater than B12, and so on. Okay, so if A and B are both totally positive, then everything in between will, in this order, everything in between will be also totally positive. So, but it relies on already having a pair. Yeah, and then there are some small perturbations that you can achieve. For example, in the element, if you add something to 1, 1 or n element, it will remain something positive. It will remain positive and so. Huh? Yeah. Yeah. Yeah, exactly. Yeah. So maybe, since there are no questions, maybe I'll just do a little bit of a preview for tomorrow. Right? Not. Yeah, I will repeat it. Just. Yeah. So I'm not going to write anything. I'll just say it in words. So we saw this example of 3-by-3 matrix was all 2-by-2 minors positive, but matrix is not totally positive. So there is a nice sufficient condition for total positivity, which comes from perturbing, because this is what brought it to me, perturbing this condition of 2-by-2 minors being positive. You can strengthen it, because what is a 2-by-2 minor being positive is the product of diagonal elements is greater than product of off-diagonal elements. So if you make product of diagonal elements greater than product of off-diagonal elements times something which is greater than 1, maybe this will do the trick. And so I'm going to talk about this really nice but not so well-known result about what this perturbation should be to ensure total positivity. So there is this value for this perturbation, which is optimal, and it's very nice. Result was very tricky but elementary proof, which I'm not going to give. Well, just in one direction, I will give it another. But that's what this perturbation talk brought to mind. All right. Work for me.